Hi everyone, welcome back to Workshop, and this is part 5 of the Keithley 2001 7.5 digit multimeter repair. Now if you haven't watched parts 1 to 4, I've linked them down below, well worth a look. And don't forget to check out the comments below each one of the videos. There's been quite a bit of response to this repair. Further to my last video, I have actually decided to change tact a little bit. I was planning and trying to get the original board up and running. Yes, it looks a little bit like a lot of the ICs are short circuit. It looks like that power supply failure has probably zapped just about every IC on the board. But I do have the donor board, which I originally didn't want to use because it's an older board and it looks a little bit tatty. Someone's already had a go at it by removing the electrolytic capacitors, etc. And I really didn't want to use it. However, on review of where this board came from, it came from a country that doesn't use 220 or 240 volts. They're down at 100 volts. So even if the pre-regulator part here, which I had some concerns of, which I mentioned in the last video, it looks a little bit burnt deposits in and around it. Even if that did fail, it wouldn't have put a higher voltage through onto the secondaries. There would have been no over voltage onto the secondaries. So I'm probably in a good position in regarding everything downstream of the actual regulators. So I think I'm going to go ahead and start working on this donor board and using it. So taking a closer look at the donor board, I have actually measured across some of the digital ICs, across some of the DC supplies, the plus and minus 15 and the plus 5, and they look in great condition. Possibly one of the rails isn't, but when I turn the board over, you will notice, let me zoom in a second, that across the minus 15 volt rail you've got this tantalum capacitor which is clearly gone. So maybe that'll sort out the 15 volt rail, I'm not sure. There is also some residue. I don't know if you can see that on the camera there, and that looks like leakage from electrolytic capacitors. How it's ended up in a line right along there, I'm not really sure. And also the same down here. So what I'm going to go ahead and do is I'm going to remove these electrolytic capacitors. I'm going to move the two 15 volt regulators and the 5 volt regulators. I'll put in new ones of them. I've got a bridge rectifier here that's hanging out of its holes in the PCB. Somebody's had a go at desoldering that. And more importantly, the pre-regulator circuit here, I'm going to start removing the components that I don't need, and the automatic 110 240 volt selection, I'm just going to bypass that completely. Or the other option is I could maybe design a little board that could sit over the top of here and maybe on some sort of riser or something like that with a line voltage selection switch on it that I could still connect up to the primary windings on the transformer. But I'll see close at the time once I get rid of those components that I don't need. There is other components as well. These BNC connectors here look a little bit tarnished, so I'll probably swap them over as well. And one other item, this front rear switch here is just very sticky, but there's a good one on the original board. So I'll remove those components, and once I get to that stage, I'm going to stick the board in my ultrasonic cleaner. It's really quite dirty and grimy. So let me get on with that. Let me start removing some of these components here, and I'll come back. Okay, I've removed a heap of components, and here's my little collection here. And the first thing was the electrolytic capacitors here. Yeah, they're wet underneath, so yeah, they've been leaking. Luckily, no damage to the PCB at all, although it's quite wet, so I will need to get that cleaned up. I've also gone ahead and removed quite a lot of components from that main switching circuit there, and I've removed the regulators there, and I think I'm ready to start testing the resistances across those regulators, and let's see what we get. Now, I did pose the question in the comments in the third video asking if anyone happened to have their 2001 in bits. Maybe they could measure the resistance across those DC regulators, the output from those regulators down to ground. And one kind person replied, and he's getting across the plus 15 volt regulator 83 ohms, which is quite low, but this is a working 2001. He's also getting 500 ohms across the minus 15 volt rail and 600 ohms across the 5 volt rail. So I haven't done it yet. Let's measure across my rails and let's see what we're getting. So here we go, the plus 15 volt rail first, which is this here, and I'm getting 67 ohms in comparison to his 83. That's not too far off. And now the minus 15 volt rail, which is this two here, I'm getting 2k and he was getting 500 ohms. Well, I'm quite a bit more than 500 ohms, but it's better than being quite a bit less. And the positive 5 volt rail, which is this two here, I'm getting 920 ohms and he was getting 600. Now, of course, different brand of ICs, etc., can all have an effect on those resistances, so I was not expecting to be spot on, but to tell you the truth, I'm quite happy with that. I would put power into this board given the resistances I'm measuring, and of course I don't have the actual regulators fitted, so it would change a little bit. So the next thing I'm going to do, I'm actually going to clean up the board now. Yep, I've got those leaky caps there, but if you take a look over here, so you can see there's quite a lot of dirt in and around those components there. That's not blast damage from a blown IC, that's dirt, and I think it's no coincidence because it's right next to the fan at the back of the unit. So as it was pulling air down across this part of the board here, it's probably taking rubbish and dust and everything from the outside and depositing it right across the board there and out the fan, and some of that dust has found its way underneath some of those ICs, and in fact some of those tracks here have a line of residue attached to the top of the track. It almost looks like the track is vaporized, but I don't think that's the case. I just think it's dust attached itself to those tracks when, you know, when power was in it. It's maybe attracting the dust, that fine layer of dust, and you can see that fine layer of dust as well in and around here as well. So I'll get the ultrasonic cleaner out, and I think I'll give this board a good old clean. And there's the board completely cleaned off and totally dried, and it's made quite a difference. Especially around this area up here, where all that dirty marks were, there's still a little bit of staining on the PCB, but nothing like it was, and everything's totally dried off and ready for testing again. And whilst I had the meter out, I thought I'd take a look at the A to D boards. I've got my original one here and I've got the donor one here, and I just wanted to see if my original one was shorted out across the power supply as well. Now luckily across the back, well, there's a few tantalums that are probably across the various supplies that come up to this board. I think we've got plus 5 volts and plus and minus 12 volts, so it must get its 12 volts from somewhere down on the main analog board. But let's take a look at the plus 5 volts. It's got a digital ground next to it, which I'm presuming, so it's 173 ohms, there, and on the donor one 101 ohms. Wow, so the donor one's actually a little bit lower. And then we've got the plus and minus 12 volts. Let's take a look at that. So the plus 12 volts is at 18k, minus 12 volts around about 18k as well, and the same on the donor board, 56 versus 25. So at the moment there doesn't look to be any dead shorts across the supply lines to the A to D. And so the next thing I'm going to do is I'm going to fit all the electrolytic capacitors. I've got new ones to fit. I'm not going to fit the regulators just yet because I want to feed my own plus and minus 15 and plus 5 volts from the bench power supply and do some probing around, and let's see if I can get power to the board without the currents going sky high. The AC side, the transformer, I'm just leaving for the time being. And I'll also fit the front rear switch because I'd removed the faulty one from this board. It was sticking real bad. And I'll take the one off the original board and fit it because it's pretty good. So let me go away and do that now, and I'll come back. Okay, and moving on, I've done a little bit more work and I've been preparing the board for first power up. I've fitted all the new capacitors there. There's one over here that I don't need because that's on the pre-regulator 220 110 volt selection, and that's all been removed, as you can see. And there was a bridge rectifier down here for the 5 volt supply. The original one I've got, but on this donor board it was desoldered, so somebody had obviously had a go at trying to remove it from the board, but just hadn't actually pulled it out. So I don't trust it. Maybe they've detected a breakdown in it or something like that. The 4 diodes inside it do seem okay, but I don't trust it, so I've fitted one of my own ones there. Now I don't have a round bridge rectifier in stock, so I've managed to retrofit in one of these 6 amp, small 6 amp ones, which is more than good enough. I've also been cabling up the DC supplies here, bypassing the regulators. So I've got my plus and minus 15 volt here and my plus 5 volt, and it's a shared common between the 3 rails, so that's fine. And the BNCs over the right hand side here, that's off of my board as well, just purely because the ones off this donor board were all tarnished and probably a little bit corroded inside, so I wanted to use the nice shiny ones. Everything else seems okay. I did inspect underneath the capacitors before I fitted them, and there's no broken tracks, and the corrosion from the leaky capacitors didn't seem that bad. It just slightly marked the top of the PCB there, but hadn't actually damaged any of the tracks. I'm going to use my BB3 power supply. It's my go-to power supply on the bench here for things like powering up boards for the first time, because I've got good control over the 4 channels in the board here. I'm just going to be using the 3. I've got the channel 3 is going to be used for the 5 volts, and channel 1 and 2 I've hooked up for my plus and minus 15 volts, as you can see here with the cables here. The one interesting feature on this power supply is that it does have some digital inputs on the front panel here, and I've managed to wire up a couple of switches there, and these are user configurable. You can put scripts on an SD card in the front here and write them for all sorts of things to run Skippy commands, etc. on the power supply. So I've gone ahead and written a script in order to make use of those 2 buttons, and if I just load up the script, I'll show you what it does. Go to the file manager, into scripts, and I've got an on-off script that I've written there. So that's it running, and basically if I just hit this switch here, all channels go off. Hit the other switch, all channels go on. And the idea behind that is I can put this switch nice and close to where I'm working, so that if ever any of the channels in the power supply suddenly start running away by some problem on the board, I just need to hit this button, emergency stop in other words, and it'll turn all the channels off. So we're all ready to go. I've got it all cabled up. We're all ready to power up. I've set the plus 15 volt rail to 200 milliamps max, the minus 15 to 200 milliamps, and the plus 5 volt to 300 milliamps. I've got no idea what sort of power this board's going to draw, but those are quite low settings there, and it should highlight any problem if there is one. So all I've got to do now is hit the button, which I'll do off camera, and we'll see what happens. Okay, go. Okay, and we've got plus and minus 15, 150 milliamps for plus and minus 15 volt rail, and we're pulling less than 250 milliamps on the 5 volt rail, so it's got power. So power is on, so I'll go over the test points at the left hand side of the board here. Starting with a plus 5 volt, I should get some volt drop across all these long cables, but we'll see how it goes. 4.9 volts for the 5 volts, 14.9 for the plus 15, and minus 14.2 for the minus 15. Okay, I've been going over some of the schematics, and there are some other voltages I can check. The plus and minus 8 volt supply come from that unregulated supply, so I'm not going to be able to hook that up at the moment, but I don't think there's a problem in powering up without them. There is a minus 5 volt rail here from a 79LO5 that comes from the minus 15 volt rail, so let's check that out now. So that's across C502, and C502's here. There's the 5 volt regulator there, 79LO5 and SOIC package, and yep, minus 5 volts spot on. And just for fun, how about the voltage reference from the LM399? Well, that's on pin 6 of this IC here, I think. So 3, 4, 5, 6. Should be about 7 volts. Oh, it's not. 1.8. Wow. Okay, after a little bit of digging, looks like I won't get the voltage reference until I've got the digital board connected. There's a bit of logic behind that as far as I can see. It needs some commands to switch on some transistors in order to enable that. So that can wait. And so far so good. So I think right now I'll look at the A to D board. I've got a choice of which one I want to plug in, but I think I'll plug in the one that paired with the donor. Let me go away, set that up, and we'll come back. So here's the A to D board. I have actually checked it out in terms of short circuits and everything like that, and there's no short circuits that I can see across any of the supplies. Well, here's something curious. It was just a way to plug in the A to D board. I noticed on my original board that the board is annotated right down the side of this connector here, which pins which, and there is actually a plus and minus 12 on the 5th and 6th pin from the bottom there. So I did actually go and measure on my connector here on this donor board, and it's plus and minus 15. So I don't know if there's a difference between these two boards, because this donor board here, this donor A to D, is paired with this analog board here. However, you know, they do look more or less identical. I don't see any differences really. So I think I'll need to go and have a look at the schematics and look up that plus and minus 12 volt here, and maybe it's just a screen printing problem on this A to D board. Who knows? And here's the schematic for the A to D board, and it's very clear, plus and minus 15 volts going down to pins 5 and 6 of that connector there, and it's basically used just to power a couple of op amps or 2 or 3 op amps on the A to D board. So I'm going to go ahead and plug in the donor A to D board, and we'll see what happens. Okay, ready for a power up off camera. Now I'm expecting a little bit more current consumption, so I'll need to keep my eye on current limits on the power supply. Yep, and it looks like the plus or minus 15 volts will need up slightly, and the 5 volts as well. So let me just go ahead and do that. And there we go, I've got power up now, and I'm at 180 milliamps for the plus 15, 175 for the minus 15, and 290 for the 5 volt rail. And actually I can measure the VREF now, the LM399, because the signal actually comes from the A to D board. So if I can just get my probe under this board here, I'm measuring 6.902 volts for the LM399. So that's spot on. Now, a couple other voltages I can measure. There is actually another voltage reference underneath the A to D board that I can't get to, that's only active when the A to D board's plugged in, and I think that's a positive 1.75 VREF. Can't get to that, but there is one marked up on the A to D board itself. It just says minus VREF. Don't know what it's meant to be, but I'm getting minus 10.32 volts, and what it's supposed to be, I don't know. Okay, and back to the pre-regulator circuit here. You can see that I've cleaned up the board, especially underneath those ICs, etc., where I've managed to use my fiberglass pencil and just clean up the area underneath those ICs as best as I can. And it doesn't look like at the moment there's any broken tracks or any corroded tracks, so I should be in good shape. Now, of course, I won't be fitting the relays. I will be bypassing them with links. That shouldn't be a problem, but I will need to refit the components that are actually used for the pre-regulator, like the MOSFET, the bridge rectifier, and the resistor, etc. Now, you could be asking, why not bypass the pre-regulator as well? Well, I think there's a good reason for that, and I did do some testing and I did look at doing that. Let's look at the schematic. So as I showed in my last video, here is the pre-regulator circuit itself, and you can see there's the MOSFET and that 470 ohm resistor that I explained how that worked previously. So what I went ahead and did was I took the transformer and I just hooked up 240 volts to it across the outer windings there, and measured the AC outputs on the secondary just to see what I was getting. And the reason I was doing that is I wanted to see that in normal operating mode, is that MOSFET completely switched on and therefore effectively short-circuiting the positive and negatives on that bridge rectifier. If that was the case, then I could probably do away with the pre-regulator and just wire up 240 volts across the primary and off we go. Well, looking at the outputs that I was measuring on the secondary with 240 volts going in, they're all too high, which leads me to believe that MOSFET is never switched on fully. It's always limiting the current along with that resistor. And I think I've worked it out that in order to get the secondary voltages that I think would be necessary on the output of the transformer, I'd be looking at somewhere around 170 to 180 volts across that primary circuit there. And obviously, putting 240 in there, that's not going to work. So I'll definitely need to go ahead and put the pre-regulator components back on the board and get it operational. Now, I've not got too much of a problem with doing that because the pre-regulator can only ever reduce that 240 volts down. It can't step it up. And there's the components I need fitted for the pre-regulator. In fact, some of the pre-regulator circuitry is actually on the digital boards. We'll take a look at that in a second. But this is all I need on the main analog board. You've got the connector here for the secondaries. You've got the main photocoupler with the MOSFET and the big 470 ohm resistor, power switch, mains AC input, the bridge rectifier on that input, and the fuse obviously. And I've also linked out the relays so that I'm basically selecting the two 220 or 240 volt tap on that transformer there, on the secondaries there. All this other circuitry I don't need. So let's take a look at the schematic and see why I don't need those parts. And here's the photocoupler and the MOSFET and the big 470 ohm resistor. All these parts here are to do with the high-low selection, the 220, 110 volt selection, so I don't need any of them. Some of them are left on the board. I don't see any harm with that at all. I'll probably lift R123 and R250 just to stop this part of the circuit here getting any power. And of course these three relay contacts here I've jumpered so that I'm basically getting 240 across the outer taps of that primary side of the transformer. So this is the high-low control, the 110 volt, 220 volt selection, and the high-low control. I don't need any of this. There's that LM311, the LM317 producing that 8 volt supply, the 555, the optocouplers. None of that's needed at all from what I can see, because ultimately all it's doing is driving relay 1 for the 220 110 volt control, and also relay 2 for the high-low control. I'm gearing towards powering up, but I'm trying to test all the individual parts of the pre-regulator circuit, and what I would like to test is this control signal here that controls this optocoupler, which controls the MOSFET here. I need to know where this is coming from and how it's working, and try and make sure it's okay. This signal here, cont, comes from the digital board. Let's take a look at that. And here's the digital board. Please excuse the annotations, it's just to keep me clear as to how this thing works. So what you've got is secondary coming in here from a transformer, a bridge rectifier, there's that large capacitor on the digital board. You've got a voltage doubler circuit here which is feeding a 5 volt regulator, providing 5 volt for the integrator and a comparator on this part of the circuit. Now fed off of that unregulated supply from the output of the bridge rectifier is a voltage divider, divide by 3, and that basically feeds one of the inputs on this integrator. The other input on the integrator is basically the 5 volt supply divided by 2, because you've got a voltage divider here. And so basically the integrator is monitoring the voltage across this large capacitor, this unregulated DC here. And as it goes up and down, it can turn off this FET here, which basically turns on and off the control signal. So I can simulate this. I've not hooked up the AC yet, but I put in an unregulated supply coming in here, and I can vary that up and down, obviously giving it enough to provide 5 volt regulation, and I can vary that up and down, therefore varying this signal here going away off to the integrator. And if I wind the voltage up, I should be able to see this FET switching. And so here's the digital board, and I've just hooked up an LED, a series resistor and an LED to that control output, i.e. the output from that FET, which is down here. And I should be able to vary this supply, this DC supply here, coming into this large capacitor here. I should be able to vary up and down and watch that LED go off and on. Now why use an integrator? There's the actual integrator IC there. Why use an integrator? Well, if you just used an op-amp or something like that, then it would switch too fast. You'd end up getting a chattering on that control output as noise on this unregulated DC supply went up and down. It would end up causing this control signal to chatter. So by using an integrator with a large capacitor, which is down here, then you're able to slow down the operation of that output from the integrator. I'll try and demonstrate that now. So I've got my power supply hooked up. I've got it set for about 7 volts at the moment, and it's enough to provide a 5 volt supply for that part of the circuit. And if I wind it up to something like 11 volts, I think I managed to get to, and you should see this LED turn off. And then as I wind it back down again, it will come back on. So just let me put on the power supply off camera. And there it is, you can see the LED is on and I'm set for 7 volts, so I've got power to the digital board. And if I just wind that up now to 11 volts, you see the LEDs going off and then back down again to 7 volts, the LEDs come back on. So I know that this circuit's working now. So I hadn't replaced any of the ICs on this part of the circuit, and I did actually want to test it to make sure that control signal's working before I hooked it up to the analog board and obviously the transformer. But it seems to be working great. Well, we're getting pretty close. I think I'm ready for a full-blown hookup. All I've got to do is fit the 5 volt and 15 volt regulators to the analog board here. I've got the small heat sinks all ready, digital boards ready, the displays ready, and the transformer sitting here as well. So I should be able to power up on the workbench like this. But that's for another video. But don't worry, it won't be too long. It'll be this weekend. But hopefully in the next day or so I should have a Keithley 2001 powered up. Fingers crossed. Thanks for watching.